One of the most important skills you can learn in a chemistry course is that of dimensional analysis. It is used widely throughout the course. Dimensional analysis uses conversion factors to change one quantity to another. A conversion factor is a fraction where the quantity present in the numerator and denominator are the same amount but expressed in different units. For example, 1 foot is the same length as 12 inches. This equality can be used to write a conversion factor. It can be written as a fraction where you have 1 foot over 12 inches, or you can write the reciprocal of that, 12 inches over 1 foot. Dimensional analysis makes use of the fact that we can cross out items that are both in the numerator and the denominator. For example, if you were in math class and we had 3/4 times 1/3, the 3's could be crossed out because a 3 in the numerator over a 3 in the denominator, 3 over 3 is 1. You can do this with numbers. You can also do it with labels. Let's look at an example. How many yards are there in 17.8 miles? One of the first steps when we do dimensional analysis is always to write the given number, 17.8 miles. If you want to abbreviate miles, go ahead, but please don't use M because that would be meters. I've never had to memorize for any course how many yards are in a mile, but I do know how many feet are in a mile. 5,280 feet for every mile. Using dimensional analysis, I know that for every 1 mile, there are 5,280 feet. I've chosen to put miles on the bottom so that they will cross out. And right now, if I stopped and multiplied 17.8 by 5,280, I would have the number of feet in my given measurement. However, it doesn't ask for feet, it asks for yards, so I'm going to continue on. I also know that there are 3 feet in a yard. So I will put 1 yard over 3 feet. And again, I've chosen to write it this way so that the feet will cross out. At this point, you can grab your calculator and multiply 17.8 by 5,280 and divide by 3. So essentially you multiply across the top and divide by what's on the bottom. The answer you get on your calculator will be 31,328 yards. When we are rounding when doing dimensional analysis, it's very important to distinguish between exact numbers and then measured numbers. 3 feet in 1 yard is a definition. I didn't measure the fact that there are 3 feet in a yard. It's simply defined that way. The same thing with 5,280 feet in a mile. That's a definition. It's not something I measured. And so there's no uncertainty in either of these conversion factors. In fact, they are both considered to be exact numbers. And they have unlimited sig figs. So we don't look at those numbers to determine the sig figs in our answer. We instead come back to our given number, 17.8 miles, the measured quantity. 17.8 has 3 significant figures. So we need to take our answer and round it to 3 significant figures. I sometimes have students who will write 313 as their answer. 313 does have 3 significant figures, but it's certainly not close in length to 31,328. So we have to keep in mind that we're rounding to 3 significant figures. So I would keep the 3, the 1, and the 3 will stay a 3 because there's a 2 after it. So our answer to the proper number of sig figs is 31,300 yards. You could also choose to write this in scientific notation, 3.13 times 10 to the 4th yards. Either would be acceptable. As you are learning the method of dimensional analysis, it's important to understand the method. Many of you would be able to solve this problem on a calculator or to just press a button on your calculator that would just do the conversion for you. What we want to do is start with some of these examples that have units that are familiar to us so that later when we get to things like moles and kilojoules and units that aren't as commonplace, we'll be able to fall back on this method of problem solving. Let's try another example. How many seconds are there in 2.75 years? As with any dimensional analysis problem, we want to start by writing our given information first. 2.75 years. Years could be broken down into many different quantities. We know there are 52 weeks in a year. We know there are 12 months in a year. The issue with using something like months is then the next step would be a little problematic, because for each month of the year, well, they don't all have the same number of days. Some of them they all have 28, but some of them have 30 or 31. So we instead are going to go with days. So 2.75 years, I'm going to take 1 year and break it into 365 days. And then we know each day consists of 24 hours. One hour is 60 minutes. And 1 minute is 60 seconds. If you take a look at the labels, years cross out, days cross out, hours are gone, and so are minutes, leaving seconds, which is the desired unit. Again, if we crunch the math out on our calculator, we would have 2.75 times 365 times 24 times 60 times 60. Our calculators would read 86,724,000. We now need to round to the proper number of sig figs. Each of the conversion factors we've used, 24 hours in a day, 365 days in a year, and 60 minutes in an hour and 60 seconds in a minute, are all definitions. Therefore, they are all exact numbers. They're not measured numbers. 2.75 is the measured quantity and the number we should look at for significant figures. It has 3 sig figs, so we need to round to the place value where the 7 is, the hundred thousands. So it would be 86,700,000 seconds. If you like scientific notation, you could also report your answer as 8.67 times 10 to the 7th seconds as well, and that would be also totally acceptable. Let's take a look at another example. You are caught speeding within the city limits and are clocked at a speed of 42.8 miles per hour. How many meters per second is that? When you're in a chemistry class, writing miles per hour as mph isn't very helpful. So be sure to list miles per hour as a fraction. Miles in the numerator, hours in the denominator. We are trying to convert miles per hour to meters per second. So we have a length unit, miles, that needs to be changed to meters, and an hour or a time unit that needs to be changed into seconds. It doesn't matter which one you start with, but since I was given this conversion factor in the problem, I'm going to choose to start with that. 1 mile is equivalent to 1.609 kilometers. In order to cross out the miles, I'm going to put that on the bottom, 1.609 kilometers on the top. I eventually want to get to meters. So if I use my metric prefix knowledge, kilo means 1,000. So 1 kilometer is equivalent to 1,000 meters. So that will be the conversion factor that I use next. Be very careful. I've had many students who write 1,000 kilometers as equivalent to 1 meter. And if you think about those two quantities, they are certainly not equal in length. So make sure you have the 1,000 in the proper place. If I stopped right now, I would have meters per hour, but I need meters per second. So I need to work with that hours next. Now notice hours is in the denominator, so I'm going to need to put it in the numerator in my next conversion factor. 1 hour, 60 minutes, and 1 minute is 60 seconds. At this point, hours will cross out and minutes will cross out, leaving meters per second. And so to solve this one on your calculator, we want to take 42.8 times 1.609 times 1,000, and then I like to hit enter or equals, divided by, you can either use parentheses 60 times 60 or divided by 60 and then divided by 60 again. We should come up with, if we're looking at 3 sig figs in our given number, 19.1 meters per second. So this is an example where your label to begin with is a little more complicated. It's known as a complex unit because it's more of a fraction than rather just a regular unit. In this next example, the complication comes in from the fact that we have a cubed unit. The question says how many cubic centimeters are in 1 cubic meter. If I look at a cubic, or if I just look at how centimeters and meters are related, we know that 1 meter is 100 centimeters. So many students will set this up and write the fact that, okay, in 1 meter there's 100 centimeters. And then they look at the cubed part of the meter measurement and they simply add a cubed on the meter and a cubed on the centimeter, and then they tell me that their answer is 100. The problem is they have forgotten to cube the 100. And so if you like to write your cubed units in this fashion, be sure that you cube the number and not just the label. 100 cubed, since it is 10 to the second and then cubed, would be 10 to the 6th cubic centimeters, or you could write it as 1 times 10 to the 6th cubic centimeters. Either way, there would be 1,000,000 cubic centimeters in 1 cubic meter. Another way to work with cubed units is, instead of writing the unit as just the cube, is to expand cubic meter to be meters times meters times meters. Then if we use our conversion factor that 1 meter is 100 centimeters, when we write that, that will only take care of one of our meter measurements. And so if we do it 2 additional times, then we can cancel out the remaining meters. This will also yield an answer of 1 times 10 to the 6th cubic centimeters. Mathematically, the approaches are both the same. It's just a matter of how you want to write the units. You should pick which method works best for you, as long as you remember to do all the parts. We'll finish with 2 last examples. Find the mass in grams of 2 gallons of water. and in the problem they give us the conversion factor that 1 gallon is 3.785 liters. What I'd like you to notice about this problem is that we have a mass, M, and we have 2 gallons, which is a volume. In class, when we've been talking about mass and volume, it usually is with something involving density. Now notice that is not included in the problem. And a key thing to watch out for as you are working these dimensional analysis problems is the textbook, or in a textbook problem or on the test, they may assume that you know the density of water and would have that to use in these problems as well. And so even though it's not stated in this problem, we are going to need the fact that density of water is 1 gram per milliliter. And so if you see a problem with mass and volume, just kind of keep in the back of your mind that density may be needed as well. In this problem, we're looking for mass. So if I have density is mass over volume, if I rearrange that, mass would equal density times volume. So if I start with my density, 1.00 grams per milliliter, and I multiply by 2 gallons, we can see that really our units don't cross out at all in terms of dimensional analysis, so we need to do some further work. I'm going to make use of this conversion factor. 1 gallon is 3.785 liters, placing 1 gallon on the bottom so that it will cross out. At this point, gallons will go away, and I would have grams times liters over milliliters. Now when you're looking for mass, an appropriate mass unit would be grams. So if I can somehow resolve the issue with volume, then I should be in business. A liter contains 1,000 milliliters. So right now I have liters on the top and milliliters on the bottom. So I'm going to place 1,000 milliliters on the top and 1 liter on the bottom. This way liters will cross out and milliliters will cross out, leaving only grams as the unit. So on your calculator, if we take 1 times 2 times 3.785 times 1,000, we should get 7,570 grams. And our given information, 2.00 gallons, had 3 sig figs, and 7,570 also has 3 sig figs. So that would be a correctly reported answer. Our last example also works with density. It says find the mass of gold plate 5 micrometers thick, deposited on a 1 foot by 1 foot surface. Express in convenient units. The density of gold is 19.32 grams per cubic centimeter. In the last problem, we used density, mass equals density times volume. The complication in this problem is that we do not have our units in very convenient, they're not in convenient labels to work with throughout this problem. If you take a look at the density, it is 19.32 grams per cubic centimeter. To get the volume, I'm going to have to multiply length times width times height, or length times width times thickness. The units on density are grams per cubic centimeter. So our volume, in order for these units to work out properly, our volume will have to be in cubic centimeters. Right now, if I multiplied the 3 dimensions, I would have feet times micrometers, which wouldn't definitely not equal cubic centimeters. So you may need to do a little side work or calculation first. 1 foot, if you consult a table of conversion factors, is equivalent to 30.48 centimeters. So we know each of the 1 foot by 1 foot sides would instead be 30.48 in terms of centimeters. When you're looking at 5 micrometers, 5 micrometers, if I know my metric prefixes, micro is 10 to the negative 6th. So I could write this as 5.00 times 10 to the negative 6th meters. At least that's in the metric system, but it's not centimeters yet. There are 100 centimeters in 1 meter. So in terms of centimeters, this thickness could be expressed as 5 times 10 to the negative 4th centimeters. So now, if I go back to my setup at the top, I have 19.32 grams per cubic centimeter times, remember, volume is going to be length times width times thickness. So 1 foot I'm going to express as 30.48 centimeters. The width also 30.48 centimeters. And the thickness 5 times 10 to the negative 4th centimeters. Now our labels will work out much more nicely because I have centimeters times centimeters times centimeters, which is centimeters cubed. So all 3 of those can go away with the centimeters cubed in the denominator on the density. And that will leave only grams, which is a very appropriate unit for mass. Multiplying all of this together, 19.32 by 30.48 times 30.48 times 5 times 10 to the negative 4th gives me 8.97 grams. This concludes our work on dimensional analysis.